In this chapter, we will see simple frequency response for all the amplifier stages. This is a simple common source amplifier loaded with CL. So DC gain will be GM RDS, and each bandwidth with 1 over RDS and CL. So here bandwidth and DC gain is defined. Since this is one pole at the output, it will go down by minus 20 dB per decade. This is called the single pole roll-off. The phase shift at the pole frequency would be 45, additional 45 degree shift. So this will give us the lagging delay. So if this is this common source, the phase of the input and an output is inverted. So as you can imagine, if you increase the input voltage, the current between drain and source will increase. That will bring down the output voltage down. So initially, without CL, I mean this input phase would be 180 degree. The phase inversion is there. The additional phase shift is 45. So you have to consider that this 0 degree is actually the minus 180. But in a typical amplifier design, so this additional phase shift delay out of this pole give us a typical amplifier. So additional delay or phase shift is observed by the pole, right? So when you apply the input sign like this, typically without delay, the output will be like this, just phase inverted. But with the pole, so it depends on the input frequency you apply. So at the low frequency, you are getting like this, the 0 delay, just phase inversion. But if you increase the frequency, like this kind of a minus 90 degree shift frequency there, then it will, the higher frequency like this. So if you apply the let's say apply the more higher frequency like this, so 90 degree shift like this. Here, so originally like just inversion, but little shifted, 90 degree shift will be difficult. It's quite difficult to draw here, but you can imagine like so this is high frequency. If you zoom in like this, and then output like this, supposed to be like this, but it is delayed by 90 degrees, so it actually comes out like this, right? So this is in a 90 degree. Okay, this is how you interpret this. The one thing that most important to remember is that once we know the AV, DC gain, and bandwidth, we can always find the GBW, gain bandwidth product. The gain bandwidth product defined by gain times GM RDS times 1 over 2 pi bandwidth RDS CL. By having this, we are canceling out the resistive components. So that gives us GM over 2 pi CL. So surprisingly, as you can imagine, the amount of RDS affecting DC gain, but it doesn't affect the GBW. It only affected by GM, transconductance, and load capacity, CL. So this is quite important. So GMCL. So you can think of this circuit analysis for the small signal V in. The current will go out GM V in. This older current will flow through the CL, you can imagine, because at high frequency the RDS is a lot greater than 1 over SCL, impedance of the capacitance. So you can think of the current, small signal current, flow through the CL, so that you can find that the output voltage will be at midband. Output voltage will be minus GM V in times 1 over SCL. So V out over V in is minus GM SCL. This is one simple approximation to find the gain at the midband frequency. In the previous example, we only considered the pole at the output side, but in reality, there's also pole at the input. Any driver, we assume that the equivalent, Thevenin equivalent circuit here, you will have a finite source impedance RS. So we have a input capacitance CGS, right? Shown in here. So overall DC gain is the same because the at DC this low pass filter, it just pass our signal. So GM RDS is the DC gain. So GM RDS shown in here, and the bandwidth is given by RS and CL. So this is the 1 over 2 pi RS and CGS here. So gain bandwidth product would be GM over GM. This FU unity gain frequency would be GM over 2 pi CGS. So this GM over 2 pi CGS is defined by what? Omega t. So this is the this is the FT, the transistor transit unity gain frequency there. Oh, that fact RDS. Oh, I'm sorry. R times this times RDS. I'm missing this factor RS. So this time RDS over RS. So this is the unity gain frequency there. So to have a higher unity gain frequency, it requires a high FT device. So smaller the input capacitance, we get the better bandwidth at the output. So in reality, what you really need to care is this frequency, because at high frequency you will see some of the gain around here at midband, but once your input frequency go beyond that point, you will get any signal going into the amplifier. So overall character, so most of the students just only focus on the DC gain, but in reality, the DC gain and also this midband frequency gain is also important, especially for the RF application. Your desired signal is only at the certain high frequency band, like this band. So we are getting the gain only this this slope. So we want to maximize the what FT this unity gain frequency, this GBW. So we want to improve the GBW rather than just DC gain, right? Just DC gain doesn't affect the high frequency gain. What you have to do like this, either increase the GM or decrease CGS, right? And also typically the RDS also better to be larger in this example, right? RDS is going to be larger and RS better to smaller, right? To make this the GBW higher, right? At the input side, not only the CGS, also there's the CF between gate and drain. There is parasitic capacitance CF there. So if you remember, there's some overlap capacitance between gate and drain, right? So COV. There is always finite capacitance. Okay, because of there's also metal connected onto the drain, and between gate and drain there's always capacitance between two metal. So you can imagine always there's a certain kind of parasitic capacitance. So this parasitic capacitance will also affect the input bandwidth. So DC gain is GMRDS as before. So for the capacitance, we have to find out the equivalent capacitance. We know that this kind of capacitance is affected by the Miller effect. So we have a finite gain of a minus GM RDS. So the capacitance is boosted by this GM RDS. So equivalent capacitance. So if you have a CF between here and there, if we have a minus GMRDS gain, then equivalent, this is equivalent capacitance, that is grounded capacitance, that would be CF times 1 minus AV. So that is CF times 1 plus a GMRDS. So this is approximated by CF times GM RDS. So the bandwidth will be 1 over 2 pi RS times AV CF. The AV is the GM RDS. So overall bandwidth would be gain bandwidth product is the product of those two, that would give us the 1 over 2 pi RS CF, right? Because let's say show GM RDS times 1 over 2 pi and AV is the GM RDS times CF, right? So canceling out, and we have RS on the bottom. So finally 1 over 2 pi RS CF, right? So this is the bandwidth coming from the input. So this is the GBW. So this GBW, so affected by 1 over 2 pi RS CF. So this is a simple example of how we got this. So this is the Miller effect. So you have to consider the Miller effect to find the equivalent capacitance from the Miller effect. Okay, so Having Miller effect is critical, especially when you have a negative gain across the capacitor load, because if you apply the test current here, IT. So let me simply drive the Miller effect equation for your reference. For example, so if you want to find the equivalent capacitance, considering this kind of a negative gain, this is the same. For we apply the test voltage and test current here and measure the ratio between current and voltage. So if this is VT, then we have a voltage amplifier here. The other side node voltage will be what? Minus GM RDS times. Let's make it AV just here. So AV times VT. So any impedance here, there's capacitance here. So 1 over SCF, 1 over SCF. So we know the voltage difference and we know the current. So IT, relationship between IT versus impedance is the IT. Voltage is VT minus AV, VT, divided by 1 over SCF, right? So we have a VT, IT. So equivalent impedance, G equivalent, looking from the left hand side, that is grounded like impedance, G equivalent will be 1 over SCF times 1 minus AV, right? So you can simply drive that. So you can see that your capacitance is boosted by 1 minus AV, okay? This Miller cap feedforward capacitance not only introduce pole frequency, it also introduces zero. Imagine when you have how you define the zero, if the HS equal to 1 plus SO over omega G, then you can find the zero frequency shown in here. So this zero happens so when you have two separate paths, so coming in one input coming in, and you have a S over WG, some frequency dependent component is there, S over WG, then added together, then you get the zero, right? So it can be either the positive zero or negative left hand side zero or right hand side zero, depending on whether you have addition or subtraction there. So in this example, your signal coming in up until the input and then split it one path and the other path here, right? So at that point there is some two separate paths, but one path has the frequency dependent component like a 1 over SCF. So you can find that the zero frequency at a certain frequency, the output response becomes zero. So to find the zero frequency, so here is a signal coming in and added here the subtractive way. So one is coming in, current going in, and the other path current going down. So we are taking out the current. So we have a different polarity of the current. So we would assume can easily find that this will introduce a left half plane zero, left half plane zero. I'm sorry, right half plane zero. So the transfer function something like hs will equal 1 minus s over wg kind of thing. So to find that zero frequency, we can take it out. So apply the VT and output becomes 0. So the current would be what? VT over 1 over SC, and current coming down would be GM and VT. So this current will be same, so that the net current coming out would be 0. So VT over times SC equal GM VT. So S will be GM over C. So the SG zero frequency GM over SC here. So omega G would be GM over C. So since this is right half plane 0, do we have an additional phase shift here out of this? So this zero frequency is very at the high frequency because the CF is small. So we have a bandwidth here that is the capacitance input equivalent capacitance is boosted by the Miller effect. So we have a lower bandwidth point, right? And then it goes up, and then when it get to the zero frequency, we have the flat gain response, because we have a feed forward path, right? Pass through the CF will give us this high gain. Without FG it will go down, but with FG it will get the higher gain response. But this will introduce 45-degree additional 90-degree overall 90-degree shift. At zero frequency, additional minus 45-degree. This delta is 45. Shift is applied. Okay. This looks like this right half plane 0 actually behaves like a pole in the phase domain, so that will introduce additional delay phase shift, right? So overall response will be written by DC gain times pole 1 over, so AV DC gain times 1 plus S over what? Omega P, and 1 minus S omega G. This is overall response out of such simple model that's shown here. If you plug the S equal to 2 pi omega J 2 pi omega F, then you will get that this equation, the thing. Okay. Source follower impedance, let's take a look at it. So output impedance is at DC 1 over GM, and at the very high frequency this is shorted, so this current voltage drop between gate and source will be 0, so nothing will happen through this. Only RS is seen at the high frequency. If the RS is larger than 1 over GM, we get the inductive region as shown here. So that the corner frequency is FT of the device, so GM over 2 pi CGS. At that frequency, transistor becomes become nothing. So this inductive equivalent inductance can be approximated Rs over 2 pi ft. That means Rs over omega t, that is L equivalent. And there, the larger the Rs, you get the larger inductance, and the larger the omega t, faster the transistor, we get the lower inductive behavior. So this is something that we had looked at before. The active inductor example, we have Rs here. So we may implement the Rs with 1 over Gm P here, and with some feedback we also have a 1 over Gm P. So in the middle we have a VSG voltage drop here, so additional voltage drop VSG here. So voltage drop is too large, so if you want to reduce the voltage drop, we just have a PMOS and the feedback network there. So this node is connected through the follower stage. So in AC, since this output will follow the gate voltage, seems like a connected. So this voltage, so V as a constant voltage drop VGS there. So in small signal sense, the output follows the gate. So this looks like a connected. So we have an additional diode connection here, equivalent diode connection with the voltage drop VSG shown in here. So in this example, so this will also similar inductor value 1 over GMP over 2 pi ft. In this example, the output will be only 1 VSG drop from VDD, right? So VDSN is only VSG P drop here. So that will require lower supply than the other case. So the other case we have a 2 voltage drop, 2 VSG GS, one VSG, the other atmosphere VGS voltage drop there. So it requires higher supply. But on the third example, it requires lower supply, and so it make it possible for low supply operation. So on the right hand side bottom, we have seen that before. This is differential amplifier with LC tune. So this side equivalently at low frequency 1 over GM, and high frequency midband we have a inductive component that is R tune by omega t over omega t there, T2. So they can be used for the high frequency peaking, right? So if you look at the monitor, that the output impedance here, so output impedance G out, single-ended equivalent G out will be at low frequency 1 over Gm, but at high frequency it go up, right, by the inductive. But at very high frequency, the impedance seen by the capacitance goes down. So there is some resonant frequency there, like this. So we have an inductive peaking, the higher impedance at the omega 0, 1 over root omega LC, the resonant frequency there. So we get the peaking in the output impedance. In that frequency, we can get the higher gain than the DC. Okay, so this is the way. So we call that this kind of technique So without this inductor, we will have we would have some R1 over GM, and the impedance would have going down by the capacitor 1 over SC. But with the inductor, we boost the we boost the impedance. So this is without inductor L. So this is with L. So we describe this kind of things that inductor actually tune out the capacitance in at the load, so you can boost up the gain, right? So the C is tuned out by L, right? So the high frequency response for the cascode and single transistor circuit. So we will see that the difference. So at mid-band frequency, we will see the impedance from the capacitance, that would be the small compared to RO from the transistor output. So for the input variation, the current through the transistor will be GM V in. Such current will flow through the capacitance, so the output voltage will be GM times 1 over SC L, right? So minus there, this is the AV at mid band. At high frequency, at low frequency DC, that will be set by GM RO. So this unity gain frequency would be GM, so omega GM over CL would be the gain bandwidth product GBW, or the omega U, unity gain frequency. Right? What about the cascode device? This is similar. So for the small variation, there will be current will be GM times V in. This current will flow through this cascode device and then again through the capacitor. So the output will be at the mid-band also same as V out will be GM minus GM V in times 1 over SCL. So the frequency response at mid-band would be 1 pole roll-off given by that capacitor. That would be the unity gain omega U would be what? U would be GM over CL. So AV. What about the DC gain? In the previous case, in the single transistor case, the gain DC gain was GMRO, but by cascoding you got the higher the gain GMRO times the square, right? You got a lot larger the gain, DC gain. So let me write down the right hand side. So the gain would be GM times GM of GM1 times GM1 times the impedance is boosted by GM2 times RO1 and RO2, right? So we get this kind of a DC higher gain, but this doesn't change the GBW here. So cascode has the same high frequency cascode, and the single transistor has the similar GBW, but only difference is the low frequency gain, right? For the folded cascode is also same. So for input small signal variation, only current through the M1 will be GM V in. Such current will flow through the capacitor, right? So this current can only go through the M2 because this current source is the open in small signal analysis, and also the impedance looking down would be 1 over Gm. So this current, transistor current, will flow through the M2, and then it go to the CL. So overall, the gain will be AV is big GM is GM of the 1, and then times R out, that would be DC gain, and the R out would be GM2 times RDS1 RDS2. So output impedance is boosted, and then bandwidth is like boosted resistance times the load capacitance CL, and the GBW is the same, GM over 2 pi CL. So GBW here is in frequency, right? So GBW that I showed in here in radian per second, right? The different unit I'm talking about. So as you can see, the cascode, the role of the cascode doesn't change the high frequency or mid frequency behavior gain, but it only alters the low frequency DC gain, right? It boosts the DC gain. Okay. This visualized a little bit further for yourself. So with the single transistor, DC gain is GMRDS1. With the cascode here, that gain is boosted by GM2 RDS2. So the gain boosting is done by that much, but the GBW shown in here doesn't change. So this single pole roll off, this is single pole roll off is maintained, minus 20 dB per decade. Okay. For designing high gain amplifier, you have two choices. One is either having a cascode like this, or you may cascade the device. Cascade. So this is cascade and cascode. So in DC gain, you will have a similar, but the frequency response would be different. For example, if you have a load capacitor CL there and there, what would happen? So let's look at all the parasitic. So here's small parasitic there, let's say CX there, here's CX there, parasitic capacitance. The impedance looking into here would be 1 over GM, but impedance looking into that, the drain of the M1 would be into that node would be the RO. So if you plot the frequency response and then compare, we have for the cascode, we have a starting from the same DC gain, and the dominant pole would be at the output. You have the R out of the GM times. So R out would be GM times RO square. So the dominant pole would be set by that the GM times RO, right? And then second pole, so that will be 1 over R out times CL omega, and the second pole given by 1 over GM and CX, so that would be 1 over, let's say, this pole, so pole location would be 1 GM over CX, right? There's the first dominant pole and second pole. What about the cascade case? You have a similar DC gain, but here the pole here, the first pole omega P1, first stage output pole location would be 1 over RO CX. Second stage pole location would be 1 over RO times CL. So if you have if you assume that you have a similar RO from the both transistor and similar CX, or you may have a CL a little larger, but those two poles are close. Two poles are closely placed, right? But in the cascade case, the omega P1 would be what? 1 over R out times the CL, and second pole would be 1 over GM over CX. But those two pole location is widely separated. But in the cascade case, the two poles are closely placed, so that would be what? So one and here and there, like this, pole and pole, like this, right? So as you can see, depending on the location of the pole, so it will see like a sharp transition, right? Or this, or like that, or something like that. So it is eventually, it will have two poles within, so it will have a within below. So in the cascade case, so there are two poles below omega u, right? And omega u frequency here, it always has two poles. So this kind of behavior is very bad in a typical feedback system, feedback amp. It will deteriorate the phase margin in the feedback. So we haven't looked at, we haven't discussed the stability issue in a feedback circuit, but for now we will see the difference is that by cascading an amplifier, we are putting two poles placed closely that would impact on the overall that will be very bad in a typical feedback circuit. So this is bad in feedback circuit. For the GBW, so it just vary. We cannot tell exactly if the GBW can be easily calculated as long as if the response is just one pole roll off below the 1 omega u, then the thing will be simpler. But for the cascade case, the two poles make it doesn't provide us one pole roll off. So this is the minus 40 dB per decade, but here is minus 20 dB per decade. Right? In some case, we put the Miller capacitor between gate and drain in the second stage for stability in a feedback. So we may consider this case, the amplifier versus the left-hand cascade amplifier. In the cascade amplifier, dominant pole location would be 1 over what? R is GM RO times RO. So output resistance is boosted by that much GMRO times CL. And then small here, if we consider the CX here, we may have additional pole, but the impedance resistance is so small, this will be very at this pole location on that node will be very high. So we'll consider just dominant pole for now for this cascade. For the cascade case, however, we have a dominant pole omega P1 would be at that M1 output, so 1 over resistance is RO times CC is boosted by Miller effect, so CC is boosted by the second stage gain, that would be GM RO, right? So surprisingly, the pole location, dominant pole location would be similar in cascade and cascade. What about the second pole location here would be we know that this Miller capacitance will have at high frequency CC is shorted, right? So the impedance at the output is G out at output. So let's say R out at the mid band. Let's say mid band frequency. The CC is short, right? CC low CC impedance, meaning it looks like connected, so we only see the 1 over GM2. So the pole location would be 1 over GM2 over let's say CL. In reality, there will be additional capacitance parasitic. From the sheet M2 we may, so let's say so this is CX there, will be CL plus CX. And we know that by having Miller capacitance, we have the zero right hand plane zero location is also there. That will be defined by what? Right hand plane zero would be GM2 over CC, right? So I'm not gonna recalculate that again. So omega P1 is to make it differentiate, that would be GM of the second amplifier here. So here in the cascade case, here GM is the the GM of the second cascade amplifier here, pole location. So if you plot this characteristic there, for the cascade amplifier, the frequency response is very simple, like this. This is a cascade. But for the cascade amplifier, we have a similar dominant pole. If the CC, so the omega P and omega 1 would be similar if, so omega P1. Wait a second. So cascade, and so if, so the location will be similar if CC and CL just similar, then would be we would have similar the dominant pole here. And then the second pole we would see it like this, and then we have a zero location at the higher frequency here, like this, right? Pole on zero. So it depends on whether the zero is coming first and pole later, or pole first and zero later, right? Depending on the location of a zero and pole, so we may have a different, right, frequency response, right? This is for omega P this curve is omega p is higher than omega g, and bottom is omega p2 is at the lower than omega g, right? So the frequency response is a little different for the bandwidth. So by having the compensation, purpose of the compensation here, CC, in a feedback system, we put the large CC to make sure that we have a one pole roll off, single pole roll off within the omega u. That's the purpose of the CC. So one pole roll off. The one pole roll off characteristic below the omega u is very important characteristic in a feedback system, because the each pole introduce 90-degree shift phase. So in a feedback system, if the, let's say we have A and feedback factor beta there plus there minus, so the phase shift from this point to when the signal coming back, so from here is the 180-degree phase shift there, then the loop will be unstable. So any pole, a single pole within here below the omega u introduce 90-degree shift. If the pole within the below omega u, if there's an additional pole there, then it will introduce 180-degree phase shift. That will definitely make the loop unstable. So this is kind of a purpose. So this amplifier here must have a single pole below omega u. So so this beta is the just constant. So beta is below the 1, equal to 1 for case. So this is kind of a feedback circuit requirement from there. So circuit typical amplifier used in a feedback system to generate the stable gain. So this is kind of this single pole wall of condition is very important for any feedback circuit designers. Okay, so we have not utilized this fact so far. We will go ahead and touch upon on this feedback things in our feedback circuit analysis. Okay, we will. DC gain can be improved by the cascode device like this. So the boosting factor would be GM times RD2. So additional way to increase the gain would be we cascade more, one step forward. So we cascade additional device there, then we can increase the gain, DC gain can improve. The problem is every time we stack the device, it will require minimum voltage to make sure the saturation. So it is eating up the voltage headroom for the signal. So signal cannot go below certain level to make sure that all the devices in saturation, right? So this is the limited output swing range. Output swing range is a problem. Without changing output swing range, we can have a feedback circuit gain boosting by putting amplifier here. So here we take the output voltage and voltage gain there AV, amplify the gain, and some negative gain here. AV will improve the output resistance. If the AV is minus GMRO, then AV is minus GMRO. then the output impedance would be boosted by the gain of this guy. So typical AV was the GMRO, that one was additional GMRO times the additional GMRO. So we have a GMRO cube gain can be achieved by like this, right? Here on the right hand side, the red circuit is a negative gain amplifier, common source amplifier. So this will bring up the DC gain like this in a frequency response. As you can see, this doesn't change the omega u. So GBW doesn't change, omega u doesn't change, FU here, FU doesn't change. It only boosts the low frequency DC gain, right? So if you require such high gain, then you may go for this technique. But in high frequency RF system where only your signal is at the high frequency there, then you don't need this kind of technique. So high gain required in the high DC gain is required in a typical feedback system. But we have to understand the feedback circuit principle to understand what is the requirement for the DC gain kind of things. Okay, so we will learn that in the later lectures. Okay.